I welcome everyone to this video where we're looking at the mechanism of the aldol condensation. I am Mr. Ish. Thank you for joining me. In a nutshell, you're looking here at a system where you have a strong base, you have a carbonyl compounds. They can be aldehydes and ketones. They have to have alpha hydrogens. The alpha hydrogen will be the carbon attached to your carbonyl, which will be a alpha carbon, and the hydrogen on that. You have to have the alpha hydrogen. In the presence of the base, in a series of steps, you can generate carbon-carbon bonds. That's the essence of it. You can propagate compounds by generating carbon-carbon bonds using this mechanism that I will be showing you here in this video. Again, you can use aldehydes or ketones. In this video, we're focusing here on using the aldehyde as our compounds. We're starting here with this. It's an aldehyde. You have carbon number 1, this is carbon number 2, it's an alpha carbon. You know what this is ethanaldehyde, or you can just say ethanol. This NAL, the AL indicates it's an aldehyde, the ETH indicates it's ethane based 2 carbon compound. Anyhow, this is what you're looking at, ethanol. I'm looking here at a CH3. I'm going to write this properly. This right here is my alpha carbon. You know it has CH3, but I'm going to put 2 over here and I'll bring a hydrogen here. I have my alpha hydrogen. These 3 are alpha hydrogens, but I'm focusing here at a specific alpha hydrogen. Now you're going to do this in the presence of a strong base. Your reaction would essentially involve sodium hydroxide and you can say water. But what you will see is that you will be seeing hydroxide anions floating around because of the presence of that strong base, and they would look like this. Your first step here is your enolate formation. You're going to be generating here an enolate. That's your first step. We're going to generate that. There are 3 steps. This is the first. The generation of that enolate ion. The hydroxyl anion will use 2 of its electrons. There you're seeing 6. It will use 2. In a nucleophilic attack on this hydrogen, behaving as Lewis base, it will snatch this hydrogen. These 2 electrons from this bond will go into the carbon compound. Now look. The end result here will be your CH2 and the 2 electrons right here. The 2 electrons from this CH2 hydrogen bond have now ended up over here, and you have the rest of the molecule, the aldehyde. This right here has now become a water molecule. OH plus the hydrogen, a water. Keep in mind, this right here was your catalyst, base catalyst. It has been consumed by the formation of water. I'm just erasing this, and this will have to be regenerated at the end of the reaction, and I'll show you. This right here can be resonance stabilized. I'm removing this only for the purposes of space. You know we're looking at step number 1, which is the generation of the enolate. This right here is your enolate because it has an anion. It is going to be resonance stabilized. You have a carbonyl oxygen which has 4 electrons. You can stabilize it by resonance. This negative charge by means of 2 electrons can generate a double bond. You can have shuffling of electrons, and you're looking here at a resonance structure which looks as I'm showing you. The negative charge here from carbon has ended up on the oxygen. This right here is your enolate stabilizing itself through resonance. This is what you're looking at. Keep in mind, in this very first step, the formation of the enolate, what have we done? We have generated here an enolate, which is resonance stabilized, plus water, which I erased. The water came from this hydroxyl and the hydrogen, the alpha hydrogen giving you that water. Now the next step will start from here. You're looking at this. I'm going to erase this because you've seen this. You have here as your starting reactant ethanaldehyde and a hydroxyl anion. The first step is completed. Everything here is in a basic environment. Now what we're looking at is this. I'm looking here at another compound, CH3, C double bond O, another aldehyde, and it is ethanaldehyde or ethanal. That compound over there, your enolate, will behave like a nucleophile in step number 2, which will be your nucleophilic attack. Your nucleophilic attack will occur on what? It will occur right over here. Why? Because any carbonyl compound or functional group is partial negative at the oxygen, partial positive at the carbon because of the dipole moment. The oxygen is more electronegative. It sucks away the electron density from carbon. This here is rather electrophilic, so a nucleophile can attack over here. Your nucleophile here will be your enolate. My compound here is another ethanaldehyde, as you see right here. I'm removing this because this will be the site of our attack. What will attack? It will certainly not be your carbonyl oxygen behaving as a Lewis base or nucleophile. It will be this, your double bond behaving The pi electrons of this double bond behaving as nucleophiles to attack over here. At the same time, you'll have a shuffling of electrons. These two will come down here to regenerate a carbonyl functionality. The double bond will break. Two of these electrons will break to generate a carbon-carbon bond. The carbon-carbon bond will develop between this carbon and this carbon right over here. And the step you will see is this. Remember, the oxygen here is shuffling its electrons to regenerate the carbonyl compound. What you're looking at here is this generation of that. When you have the shuffling of electrons, you'll lose two of these electrons from this, and they'll come here onto the carbonyl oxygen, as you are seeing over here. This is what it is. And my hydrogen, I'm just bringing it over here. Here's my carbon-carbon bond which has developed between this carbon and that, my carbon-carbon bond, my carbonyl functionality, and your hydrogen. There's a lot going on here, but I'll break it down for you. This is what I'm ending up here with the step number 2, nucleophilic attack. It ends right over here. You see all of this compound right over here, it's represented by right over here. You see this compound over here, it's represented over here. The carbon-carbon bond is right over here, carbon-carbon bond. These two electrons broke away to generate a bond between this carbon right here and your carbonyl carbon. At the same time, you generated a break of your carbonyl functionality to generate a oxygen with a negative charge, because it has 2 extra electrons than it normally has. 4, here you have 6. This step number 2 ends here with the generation of this. Let's clean it out so we can bring you to the end of the reaction. We have to regenerate the base. And how will we do that? We will do that in the step number 3, which is your protonation. What does protonation mean? We're going to bring a proton into this compound, and you see over here you have a carbonyl group. You had what was a carbonyl group, but it's become that. You'll bring a proton over here and you'll generate a hydroxyl functionality. Your end result will have a carbonyl functionality and a hydroxyl functionality. So how will this occur? You are looking here at a floating water molecule, and it looks like this. 2 of these electrons will attack and snatch this hydrogen. The electrons of this bond will go back into oxygen, and you will generate here your base, which is your OH minus. Your base has been regenerated, and we don't have to see it anymore. It was regenerated in this protonation step. This hydrogen will come here to this oxygen. 2 electrons forming a bond with that oxygen hydrogen. The negative charge will go away, because no longer will the oxygen be charged excess. It will be back to its normal state, but you will be developing here a hydroxyl functionality. And the water molecule has been consumed and altered to generate a hydroxyl, and you're seeing your base regenerated. This right here is our end result. And what will our end result be? You see how we've gone from this step to this step, and then we've kind of skipped something over here, or we kind of erased things. You could have put over here a water molecule, and it will complete the picture. This step over here, the nucleophilic attack, followed by the water molecule coming into the picture to generate a hydroxyl byproduct, which you see right here. And this compound completes our aldol condensation. Now we should name this. You're looking here at a carbon 1, carbon 2, carbon 3, carbon 4. On carbon number 3 you have a hydroxyl. Carbon number 1 is your aldehyde. How will you call this? You'll call this 3-hydroxy. You have 4 carbons and it's an aldehyde. You can say butanal. The Al signifies an aldehyde. You can say 3-hydroxy butanaldehyde, or you can say 3-hydroxy butanal. There's no need for you to say 1-butanaldehyde or 1-butanal, because it's understood the aldehyde carbon will adopt the lowest, therefore it will be the terminal carbon, and hence 3-hydroxy butanal is the end result, and you've generated your carbon-carbon bond as I've shown you right over here. The aldol condensation uses aldehyde and ketone compounds in basic conditions to generate carbon-carbon single bonds you can propagate. But you see here, you're looking here at a hydroxyl compound. You could technically eliminate this and generate a double bond, and then you can reduce that double bond and generate a aldehyde, which will be more saturated than what you see. What am I talking about? I'll show you momentarily, and we'll close the video with that. Picture this compound here in your head, and we'll close out with that. Our aldol condensation mechanism ended with the generation of 3-hydroxyl butanal. That's what it was. If you take this to an elimination reaction, you can form a double bond here. You can eliminate this and form what will be the CH3, CH double bond CH, C double bond OH. You know this is a result of an elimination of the hydroxyl. You're forming a double bond over here. You can call this is 1, 2, 3, 4. This right here will be 2, and then you have here butane, the en signifying that they have an alkene, then you can say butanaldehyde, or you can say butane, and then you can say al for your aldehyde. You have an aldehyde, you have an alkene, and I'm demonstrating those. Then you can take this through a reduction process. You can use your basic hydrogen and some metal catalyst, and you can reduce that, and you can do a saturated portion over there by bringing in hydrogen. You see one hydrogen here from the hydrogen H2, and then you have the rest of that molecule, which is your aldehyde. We have eliminated the hydroxyl in an elimination reaction to generate a alkene aldehyde. Then we have reduced that alkene to generate a saturated aldehyde, and you know this right here will be just butanal, or you can say butanaldehyde. We've gone from what were initial two aldehyde separate compounds, which were ethanols, ETHAN, ethanols. In the presence of, we did aldol condensation to come up over here. Then we did elimination reaction, generated an alkene aldehyde. Then we reduced that to generate a complete aldehyde with no other unsaturated areas, no hydroxy functionalities, just a aldehyde. And we've gone from an ethanol, two of these ethanaldehydes, to a single butanal by a series of reactions. The main essence here was aldol condensation. Remember the three steps, the mechanism steps I've showed you: the generation of the enolate, the nucleophilic attack, and finally the protonation step. Everything else here is extra steps to eliminate your hydroxyl functionality, eliminate your alkene, and go through and to a saturated aldehyde. That right there is the end of this video. Thank you for watching.